Hello and welcome to the May Wednesday webinar from the IEA Clean Coal Centre. My name is Benedict Brooks and I'm the Communications Officer here. Our monthly webinars are based on our technical reports, which are available from our website, iea-coal.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration. Please visit our website for details. The subject for today's webinar is non-energy products from coal, presented by Dr. Ian Reid. I will now pass you on to Ian. There you go, Ian.
Right. Thank you, Benedicte. I'm Ian Reid, and I'm an associate with the IEA Clean Coal Centre. And my background's in combustion of fuels. But today we're going to talk about non-energy products from coal. So we're not going to discuss power generation or steel furnaces. And I'm only going to say a little bit about the chemicals, as that was reported a few years ago. So it's going to be focused on carbonized products mostly, and also looking at reducing emissions from coal and agricultural applications as well. So quite a broad range of topics. Let me just go to the next slide. Yeah, I said some of this. So we're going to cover chemicals, minerals, agriculture, new materials, and pollution control. There's an established coal-to-chemicals industry providing a host of products, and I can't hope to cover many of those today, but I will talk about some trends in those industries. The main drivers behind the growth in alternate uses for coal are a shift toward electrification of energy, a rising population, and oil prices. We expect the share of energy will rise from 20 to 40% over the next decades, driven by a rise in personal electronics, electrical transport, and increased deployment of renewable energy. And this is leading to a demand for specialized products derived from carbon, for strong lightweight materials, and also minerals for electric motors and other aerospace applications. The rise in the population by about 6 million people a year is leading to a general increased demand for chemical products and other materials, but also, of course, for food and clean water. And the products made from coal have a role to play in all these sectors. And finally, the rise in oil price above $70 is leading to increased interest in making all sorts of products from coal rather than oil. And that will help the coal gasification chemicals industry, as they are in direct competition. There's also interest in obtaining minerals from coal, something that's been done in the past to obtain uranium, but now in pursuit of metals for products such as I said, such as electric motors. And finally, there's agricultural applications. So just to look at some of these in more detail, the next high volume sector after power and steel is the production of chemicals, which use about 25 to 50 million tons of coal a year. And the report only touches on these things, but I'll talk about a few trends. In the pitch chemical sector is the more established sector, producing products for the last 50 years, but that is growing by about 100,000 tons over the next 5 years, led by demand for naphthalene-based products. Although the production is rising, there are issues on the use of aromatic products. There's more scrutiny over health risks in the preparation and use of aromatic compounds. But one of the compounds was recently banned due to flammability, not aromaticity, and that's mothballs in the European Union. The coal gasification industry is mainly based in China to provide feedstock security for their chemicals industry. And the profitability of the industry is very sensitive to oil price. And as that rises above $70, it becomes very competitive. The low feedstock price compensates for a more complex plant. And production is set to rise, adding 1 million tons of polymer in the next period in Mongolia. While the industry becomes more profitable, though, there are challenges to the coal polymers industry. There's growing pushback on single-use waste plastic that's gained momentum following the Blue Planet documentary, and it's likely to impact the plastics industry generally and products from coal. The environmental impact of coal chemicals is much greater for oil in terms of carbon dioxide emission. It's about 6 times that of petroleum-based products. And that explains why there's a lot of interest in introducing carbon capture with coal gasification. And a new plant is planned of around 400,000 tons capacity. Now, as I mentioned, the chemical sector is already the subject of a published report, and so for the remainder of this presentation, we'll focus on the new and expanding growth sectors for oil coal products. The key issues are often a relative feedstock price compared to the alternatives, the complexity of the process, and the product quality. Often products are made from a single chemical, whereas for coal tar, for instance, there are many components in the feed, and that kind of implications for the final product. So these are the things we're considering in the report, and some of them I'll cover in this webinar, but it's a very broad topic. The extraction of rare earth elements is of great interest in the United States at the moment, and these elements are needed for a host of new technologies, and including renewable power generation. And there are limited economic resources of rare earth ores. This report is limited to rare earths from rock, coal, and wastes, but there's also interest in extracting elements from fly ash. We'll look at 2 emerging technologies for coal waste that would also reduce the environmental impact of existing coal mining operations. Carbon fibre is already produced from coal pitch, and we can look at some of the issues in the manufacture. The Mitsubishi are the market leader for pitch fibre, but there's growing interest from other producers to produce from coal, and that will lead to a reduction in cost. It's the increasing use for transport and aerospace that are the most promising markets. The fuselage and wings of the latest aircraft already use carbon fibre for its strength and low mass, and we're just beginning to see it coming into ground transport. And that's a picture of a carbon fibre hood on a vehicle, but these are still custom parts at the moment. To put the use of carbon fibre in context, it's competing against aluminium, where production is about 50 million tons compared to carbon fibre at around 100,000 tons. Activated carbon is of interest not only for water purification, but for removal of mercury to achieve the Minamata recommendations. There are also CCS technologies in development that may use activated carbon to absorb CO2. I'm not going to go into this topic today, given the limited time, but just to give an idea of the market size, that's about 2 million tons at up to a maximum of about $5,000 per ton, depending on the quality of material. The next topic for electrodes, I'm not going to say too much either today. It's a well-established use of carbon, but there's a potential for increased use of coal needle coke for synthetic graphite, as prices have risen fivefold for graphite electrodes over the last year, as demand has outstripped supply, and rising oil prices are affecting PET needle coke. The pictures of an industrial electrode for an electric arc furnace. Currently, about half a kilogram of coal pitch would be used per 2.5 kilograms of electrode weight, and that's consumed per ton of steel. So there's significant consumption of material in the production of steel in electric arc furnaces. Some predict the market to increase substantially above the current $5 billion market. And this is partly because of a loss in manufacturing, but also because of the increasing demand for graphite for batteries, which will be using some of the new forms of carbon we'll talk about in this webinar. And on this slide, quite a varied range of things. The first thing is the lignite agrochemicals. There's growing concern over desertification due to climate change, and that affects many countries, but are severe where the population is expanding rapidly. One example is the Sahara Desert, which has grown by a near equivalent to France during the last century, and that rate is increasing. Of course, the rising population means more demand for food production, and this is at odds with a reduction in arable land and increasing pressure on wild areas and water resources. Lignite has long provided a cheap and secure source of energy in a restricted number of countries, notably Germany. But there's now a fall in demand for lignite for power due to environmental pressures. So technologies converting lignite to improve the quality of soils might be of interest, and building a long history for using lignite that way. The last two topics are the hot topics, really, the carbon nanotubes and graphene. Carbon nanotubes, shown in the middle picture, is a tubular form of carbon, and that is a $2 billion market that is increasing rapidly. And these materials can be produced from coal gas products. The graphene is a new product, just really emerging from the laboratory, discovered over a decade ago. And although the patenting frenzy is abated, this may be the most patented material. The picture illustrates a single atomic layer of interconnected six-member rings of carbon arranged in a plane, giving the material unique properties such as water impermeability and transparency, as well as great strength. So if we consider the rare earths coal as a mineral resource, there's been much news on rare earth elements and their importance in a host of high-tech industries. Demand is set to grow due to electrification of energy supply, and although there are rare earth deposits, there are limited economic mineral resources. The section out of the periodic table shown here shows the elements from the LIGNITE series. The light rare earths have density less than iron, and that is significant separation. And but the heavy rare earths in the darker blue, there's a slight error on the slide, are the more valuable elements. And the additional scandium and yttrium are very expensive elements, up to $15,000 a kilo. The rare earth content in coal is much less than for ore deposits, but can be over 300 ppm. The issue then is the cost of concentration compared to full mining and refining of ores that normally contain between 2% and 6%. So the first target set for this program was to achieve a 2% content of rare earth elements. And thinking about taking rare earths from rock coal or coal wastes, or after combustion from fly ash, then the main issue is whether the rare earths are with the organic or the mineral fraction, and the effect of the combustion conditions on the rare earths. For younger coals like lignite, the rare earth content tends to be associated with the organic fraction of coal, and I had expected that to mean it would be preferable to extract the rare earths from the fly ash, where there is a concentration of the metals. However, the researchers are finding that it's easier to obtain the rare earths from the weakly bonded carbon compounds rather than after combustion, where they're fused into an aluminosilicate glass. It's worth mentioning that if rare earths are removed from coal waste sources together with other heavy metals, then by default, that will mean cleaner effluents entering river systems. And so it could be a substantial environmental gain for the mining industry. The next two slides look at some ways of concentrating rare earths from coal wastes. The first method is aimed primarily at elements in tailings ponds, although it could be adapted for a range of coal wastes. There are really two stages, and this slide looks at the first part of that, to remove the carbon from the mineral resource. And this diagram shows a hydrophobic hydrophilic separation system. An organic solvent is used to concentrate carbon-containing material, and this leaves finely divided mineral waste, which would have previously been discarded, but now, of course, contains rare earth elements. Initial findings are that for mature coals, the rare earths tend to be in the rocky matter just around the coal carbon, and so that's the crucial material. The rare earth follows the mineral path and can be processed in a second stage to further concentrate material. Early results have shown a concentration of around 30 times using this process, taking the REA to about 1%. Now, this is the first step, but the second part, I'm not discussing today, but is in the report, is probably more important, as this has to concentrate the rare earths from 1 to 90%. And that plant requires multiple stages of acid and solvent extraction and also thermal treatment under acid. The ability to concentrate at these levels in a relatively straightforward way is a major step forward and uses similar technology to that found in an ore smelter. As these processes avoid ore mining costs and everything involved in the mine and are simply an add-on to a beneficiation plant, there's a substantial margin to allow for a more dilute coal feedstock. Moving on, this second technique, again, is focused on acquiring the first stage of material, is to collect and process acid mine water. This is the acidified runoff from a mining operation where the waste coal from the processing facility provides a means of gathering rare earth elements. This is a major problem from coal mining sites where the sulfide minerals present in the coal waste react with oxygen in solution to form an acid, and that acid can be as strong as lemon juice. The acid extracts the rare earths and other metals from the mine wastewater. There are many factors, I've listed some of them on this slide, that affect the extraction of the rare earths in an actual field case, and I've listed some of them. The freshwater infiltration, so it's rainwater and springs coming into the coal waste. The sulfur content, a higher sulfur level will result in more acidity. The porosity of the materials for accessing the rare earths, the effect of bacterial activity, and so on. Remedial work on mine sites involves neutralization with lime, and that forms a sludge containing the rare earths that can be refined. So this process would fit well with an environmental reclamation of a site. The key to success is to find the optimum collection point to maximize REE recovery. The concentration of rare earths from early trials is on target, and this group are also developing a main extraction plant to achieve a high purity rare earth mixture ready for smelting. In the next part of the webinar, we'll look at new materials and consider production from a range of coal feedstocks. These are mostly from carbonization processes. The first of these is carbon fibre, and here we're interested in issues around pitch fibre rather than the dominant pan fibre produced from acrylonitrile, and the picture shows a woven carbon fibre material. The applications for carbon fibre are growing, and some of the main sectors are shown on the right. The lightness and strength of the fibre makes it an ideal material for fuselage and wing construction. But a new surprising application is replacing steel and concrete. With the advent of electric transport, the demand is likely to grow due to the strength-mass ratio compared to steel and aluminium. And I've put some figures in the slide. In an electric car, the battery pack weighs up to half a ton, and ideally that needs to be compensated by reducing the vehicle weight. Currently, that's being done in an ad hoc custom way rather than by the main manufacturers. Pan carbon fibre dominates the market because of you can obtain higher quality properties, but it does use expensive raw materials based on oil. Propene is a product of steam cracking of petroleum, and that undergoes some oxidation to form acrylonitrile, which is then polymerized, and that material then provides a wet dope of pan for the carbon fibre process, which is essentially carbonization of long-chain polymers. And the advantage of using pan, as I said, is the tight specification from a single feed material. Now, where pan is a wet spinning process, the use of pitch is a melt spinning process, and I give more details on that in the report. There are fewer stages for pitch fibre processing, but there is more risk of off-spec material as pitch contains such a wide range of components, and so the carbonization process has to be more tightly controlled. The leading manufacturer of pitch fibre, Mitsubishi, may be selecting part of the pitch very carefully, as well as using very tight processing conditions. Certainly, recent independent research has shown that removing quinoline and soluble matter improves the quality of the fibres. Although pan fibre has superior properties, the market-leading dialed pitch product is now used in space applications. Moving on to carbon nanotubes, we'll briefly look at two more carbonization products. And the issue is, can coal compete with natural gas feedstock for these products? There's considerable skepticism, especially for graphene, about the product quality. There's more information on the applications and markets for these materials in the report. On CNTs then, there's been limited advance in making these directly from pitch. It can be done, but much more energy is needed because you have to break the feed molecules down to 1 or 2 atom fragments. The process shown here, the chemical vapor deposition process, normally uses methane gas, and by heating that to 700 or 800 degrees, you can build carbon nanotubes 1 atom at a time. And whereas for pitch, or even lighter components in tar, they would have to be completely broken down, and that's when you add that to the fact that there's a lot of impurities in the feedstock, is preventing us from direct use of coal tar products. But what you can use is carbon monoxide or acetylene. So carbon monoxide could be a side stream from a coal gasification plant, for instance. Moving on to graphene. This is at an earlier stage, but new products are emerging that use the thermal properties. There are LED bulbs where the graphene is used to draw heat from the light source. There's a space mirror application to eliminate hotspots, water impermeable coatings, and so on. So products are starting to come through for this. Normally, graphene is also produced by CVD techniques, when where the hot stream is passed onto a metal substrate, where again the graphene would form atom by atom. there's real skepticism on producing it from coal, but this slide shows a new process that has made 80 centimeter square a piece of graphene, and that project's out for testing at the moment. The diagram shows the outlines of the process. The coal is partially oxidized electrochemically and produces what is termed as a precursor syrup that can then be subsequently carbonized on a copper substrate to form graphene. Now, coal is bituminous coal, for instance, is made up of crystals of graphite in an amorphous, surrounded by amorphous carbon. And that amorphous carbon is more easily oxidized than the graphite crystals. And so this syrup contains small sections of graphene that then can join together on the substrate. The next stage in this process is to scale up to a full pilot operation. And it certainly competes economically with graphite exfoliation, which we've already discussed has become very expensive for electrode production. And just to show the versatility of carbon, we'll now move on to lignite as a soil improver. Up to now, apart from rare earth element extraction, we've been mainly discussing carbonization products, activated carbon, electrodes, CNTs, graphene. And this is a very different application for immature coals. It's possible to make a useful fertilizer, oil, or soil improver from lignite by mild oxidation. And in fact, that happens naturally. When lignite is left exposed to air, essentially reversing the geological processes that have taken place over millennia, lignite is in danger of becoming a stranded resource due to climate change factors, making it less attractive for power generation. And there are limited other uses. Converting it to a soil product could have a number of benefits as a means of large-scale modification of impoverished soils. The processes looking to use lignite have to reintroduce oxygen and nitrogen into the humic acid molecules, and I've shown a molecule here in this slide. It's also looking to be a low-cost feedstock for the future when compared to chemically derived fertilizers, which may also pose problems of ammonia emissions and nitrate runoff, both major problems from the agricultural sector at the moment. So a lignite fertilizer could have some additional advantages. If we just move forward. There are already products in the marketplace but these require chemical treatment of lignite with nitric acid, and that involves production of ammonia, so adding to the cost of the material. The two processes I've focused on are, the first one is a microbial conversion, and that uses a bacterium derived from termites that converts lignite to methane gas and humic acid products, which are a byproduct. And that's already marketed as a fertilizer in solution. The second is based on air ammonolysis under fairly mild conditions, an EU-funded project which is at demonstration scale now. That process has over 100 field trials in progress. Now, there are questions about the efficacy of these products, and it appears to come down to how much is applied. And for the Novahume process, the intention is to use a 15 centimeter layer of the product, which gives an idea of how much would be involved. So a significant use for lignite. So to sum up, we've covered a very wide range of uses for coal in the webinar, and of course there's much more detail on these topics in the report, but just to summarize, on coal chemicals production, it's increasing, but there are significant issues. There are HSE concerns over the aromaticity of products and flammability of traditional products. And in coal gasification, the sector is now favoured by high oil feed prices, but needs to adapt to address single-use plastic waste and address the high CO2 emission compared to petroleum products. For rare earth elements from coal, the initial targets have been achieved, and the focus is now on design of the extraction plants to upgrade from around 1% RE to 90%. The fact that RE extraction will have a side benefit to reduce mine pollution is a very important aspect, and the HSS technique reduces the potential to reduce the hazard posed by mine waste by removing carbon. On carbon fibre, there's significant potential, but the feedstock price is limiting deployment, especially for ground transportation. And coal to carbon fibre may be the way forward. The introduction and the issue for electric ground transport is the high vehicle weight is affecting the range. Demand for activated carbon is set to grow with the new application to reduce mercury emissions and potentially for carbon capture and carbon capture. There's an urgent need to lower the cost of amine-based capture systems, and so this may be a way forward. For carbon nanotubes and graphene, they can be produced from coal feeds, CNTs indirectly from coal gas or CO, but graphene has been produced after processing coal in an electrochemical cell, and that's a very exciting development. And on lignite to humates is a technology that may come forth as lignite demand for power recedes in the next decade, and issues on ammonia emissions and nitrates contaminating rivers worsen. And finally, just before I close, I'd like to mention a few new projects using coal products, just to illustrate the diversity. The first is lignite as a source of hydrogen for a hydrogen economy, which is gasification and shift catalysis to produce hydrogen combined with CO2 capture and sequestration, and that's an initiative from Japan. There's a new lower energy route to recycle carbon dioxide to carbon monoxide, again in an electrochemical technique, a technology that could help reduce emission from coal and offer an energy storage option. And finally, on graphene, there's a new product called graphene quantum dots, which is made using coal, where the feed coal dictates the size and hence the color of the graphene dots on the latest TV screens, and that's an acid oxidation technique directly using coal. So there are some very exciting developments in progress that illustrate the diversity of carbon. Anyway, I hope you've enjoyed the webinar, and I will pass you back to Benedicte.
Yeah, we're ready to take some questions now. I think there's one coming in here. So the first one is, what proportion of coal consumption does the non-energy use for coal represent?
Well, the annual consumption of coal is around 5 billion tons, I think. The chemicals is using somewhere between 25 and 50 million tons, depending on the quality. Activated carbon is using 2 million tons, and the other applications are somewhat smaller. So I would say about 1% is going to chemicals at the moment.
So there's another one here. How far has CCS got in this sector?
For CCS, that's about the use of activated carbon for CO2 capture, and that's still at a research stage. Do carbon electrodes emit CO2, and if so, what can be done about it? Well, yes, they do, because the main use for the electrodes is in the electric arc furnace, and we're using around 2.5 kilograms of carbon per ton of steel. But this is probably less than the energy for the blast steel furnace carbon use. What can be done about it? It's probably possible to capture the CO2 emissions from that process, but it requires a significant adaptation. Don't understand that one. What is the projected future demand for carbon fibre? The demand has doubled over the last 5 years, so I think we can expect it to increase at that kind of rate. But it really depends on the cost. The cost is too large for mass production of vehicles, for instance, at the moment, and that's where coal pitch products could make a difference. Is extraction of rare earths from coal purely for strategic reasons, or is there likely to be a future global supply shortage? The issue on rare earth elements, they are rare, but they are prevalent at low levels around the world. Coal mines tend to have around 30 to 40 ppm, rather than the 300 I talked about. It is strategic. As the current REs are consumed from the resources in China, then other resources might become economic as the prices rise. But the coal REE have the potential to compete with that in cost. And I think the extra advantage, the environmental benefit of extracting the REEs could be very important. I think I've covered most things. I think I've covered most questions. So I'll hand you back to Benedicte. Hold on.
Thank you very much for listening in today to this webinar. The slides will be available to download from our webinar page very soon. The next webinar from us will be on CCU, and it will be on Wednesday, the 20th of June, presented by Dr. Chen Su. Thank you so much for joining us today, and goodbye.